So what do you think so far? This is one of our easier sections, don't you think? I sure hope so. I like this section. It is fast and efficient. In 4.2.3, we're going to move on and apply our synthetic division process and the remainder theorem that we just learned to start solving higher degree polynomial equations. Given a zero, find remaining zeros. Just a quick reminder, a degree in polynomial has at most n zeros. Remember, there could possibly be less than n zeros when we consider multiplicity. Example 3, given a zero k, use synthetic division to find all remaining zeros. Notice in example A, we have a third degree polynomial function, so we can expect at most 3 zeros. That's 3 zeros, 3 factors, 3 x-intercepts. We know one of the zeros is given to be 3. Now, if I wanted to factor this polynomial, notice this one would not work by grouping. So our traditional factoring methods would not apply to this function. Hence, we need synthetic division to help us out. So what we're going to do is reduce the degree of this polynomial by dividing out the zero that we know. We are told that k equals 3 is a 0. So I'm going to put 3 in the box. I'm going to pick up the coefficients of our given polynomial. No power is missing, so we are good to go. And then run our synthetic division process. Now remember, we are told that k equals 3 is a 0. So what should I anticipate in that spot right there? Hopefully you said 0. Let's see if that's what we obtain. 3 times 1 is 3, and negative 6 plus 3 is negative 3. 3 times negative 3 is negative 9, and negative 1 plus negative 9 is negative 10. 3 times negative 10 is negative 30, and notice we do obtain the result. This, therefore, confirms that k equals 3 is a 0. So 3 is a 0, and we know x minus 3 would be the corresponding factor. Now, let's observe what we have from our synthetic division process. Remember, we began with a degree 3 polynomial, so this baseline represents a degree 2 polynomial. So let's go ahead and rewrite this as a polynomial. We'd end up with 1x squared minus 3x minus 10. Now, how many zeros would you expect to come out of this polynomial? The other 2, right? So let's go ahead and set that equal to 0, and we can solve this by factoring traditionally. This one would factor as x minus 5 times x plus 2 equals 0. So our other 2 zeros then would be 5 and negative 2. So altogether, this polynomial does have 3 zeros. They are the given 0, which was 3, and the 2 that we found, 5 and negative 2. I wrote them out of order, but that is a-okay. So on this problem, we started with a degree 3 polynomial. We anticipated 3 zeros. We took the given information, the fact that 3 was a 0, we divided it out with synthetic division, reducing our polynomial to degree 2, which is our comfort zone, right? We've studied quadratic equations extensively, and we were able to solve that remaining quadratic equation by factoring, and we found the other 2 zeros. Keep in mind, if you're uncomfortable with factoring at this point, you can also do the quadratic formula. All right, let's practice that again. This time, we're working with a degree 3 polynomial, so we can expect at most 3 zeros. We have been given 1 0. 1 0 is negative 3. Notice we are given the k value. It says k equals negative 3. So I know that the number I put in the box is negative 3. When do I change the sign? I change the sign if they say x plus 3 is a factor. In that case, I would need to set the factor equal to 0, solve for x to get negative 3. So if you're given the k value, don't change the sign, just plug that number into the box. If you are given a factor, you will have to change the sign to get the 0. Okay, but you probably already knew that. Now, let's pick up our coefficients. All of our powers are present. We'll bring down our first term, and we will multiply and add. -3 times 1 is -3. -2 plus -3 is -5. Multiplying, -3 times -5 is +15. -11 plus 15 is 4. -3 times 4 is -12, and we have confirmed that k equals -3 was in fact a 0. Now, remember, we are looking for a total of 3 zeros. We were given 1, so where are the other 2 going to come from? Well, recognize we started with a degree 3 polynomial, so these leftovers here should represent a degree 2 polynomial. That's 1x squared minus 5x plus 4. We're going to set this equal to 0 to find the remaining 2 zeros. So if we factor this, we would obtain x minus 4 times x minus 1 equals 0. So easily reading the 2 zeros, we get x equals 4 and x equals 1. Thus, we can say the zeros of this polynomial are the given value -3, also 1 and 4. Now, quick pop quiz. What is the multiplicity of each of those zeros? Hopefully you said multiplicity 1. Each one counts once, which means the graph would cross the x-axis at each of those 3 places. Okay, good deal. Pause the video if you so desire and work this problem. Then unpause the video and check your work. Okay, our job is to find all the zeros. I'm going to make an observation. This is degree 3. We're kind of picking on degree 3 polynomials here. So I'm going to expect at most 3 zeros. We'll start with the given 0 of -1 and put that in our box. Picking up our coefficients, nobody is missing. And remember, I'm going to anticipate a 0 in that last spot since we are given that k equals -1 is a 0. So running through our synthetic division, we have in fact confirmed that k equals -1 is a 0. What confirms it is the 0 in this position right here. Now, as we did on the previous examples, we started with a degree 3 polynomial, so this result should be degree 2, and we can rewrite that as a quadratic trinomial. We're going to set this equal to 0 and solve for x. Notice I'm going to get 2 other zeros out of this trinomial. When we factor, we obtain x plus 6 times x minus 3. So our other 2 zeros would be -6 and 3. Thus, our complete list of zeros for this polynomial would be the given 0, -1, and the 2 that we found, -6 and 3. A quick way to check your work is to graph the polynomial with your calculator and make sure that it crosses the x-axis at those 3 spots. All right, pretty straightforward and simple. Example 4, determine if k is a 0 of the polynomial function. So this time we're given a k value. We're not finding all the zeros. We're just going to test out that 0. Is it a 0? Which in turn means, is it an x-intercept? So I'm going to plug the k value into the box. I'm going to pick up my coefficients. Nobody's missing, so we're good to go. Bring down the first term, multiply and add, multiply and add, all the way across. Then examine that last spot. Since that last spot is not a 0, our conclusion would be k equals -1 is not a 0. So k equals -1 is not a 0. Okay, we could say though, the name of this function is g. Here's a pop quiz. What is g of -1 equal to? Apply your remainder theorem. Remember, the function value and the remainder are the same. So g of negative 1 equals 8. So we could make the observation, negative 1, 8 is on the graph of g of x. Okay, just making observations for clarification here. The problem was complete with this conclusion. Let's try the next one. H of x is this time a 4th degree polynomial function. So even though we're not finding all the zeros, if I asked you how many zeros would h of x potentially have, you would tell me expect at most 4 zeros, right? Let's find out if 1/2 is one of those zeros. So we're going to put 1/2 in the box. Now, be careful here. We have 16x to the 4th. We are missing x cubed, so we're going to put a placeholder 0 in there. We have 4x squared. We're going to put a placeholder in for x to the power of 1, and then our constant term. Remember, it's okay if you want to keep track of which coefficient you're doing. Put those up at the top. C there is for constant. Now, let's run our synthetic division process. 1/2 times 16 is 8, and 0 plus 8 is 8. 1/2 times 8 is 4, and 4 plus 4 is 8. 1/2 times 8 is 4, 0 plus 4 is 4, and 1/2 times 4 is 2, and negative 2 plus 2 is 0. So because we have a 0 in that remainder spot, we can go ahead and make our conclusion. Our conclusion is that k equals 1/2 is a 0 of h of x. That means we have a lot of information, right? We know h of 1/2 is equal to 0. Remember, this is your input, this is your output. We could also say that 1/2 0 is an x-intercept of the graph. And finally, we could take it even further and say x minus 1/2 is a factor of h of x. So if I wanted to begin factoring it, I have found one of the factors. Okay, let's finish this section with a big overview and kind of a sneak preview of what's to come. Example 5, we want to graph the given function, going over end behavior, multiplicity, y-intercept, all of those things that we've talked about before. But there's one small twist in this particular problem. We'll talk about it here in a minute. Let's begin with our leading power function. This is a good review of our previous section. The leading power function, remember, is our highest powered term. Notice this is of odd degree, which means I should expect opposite end behavior. Okay, it's going to do exactly what x cubed does. X cubed falls on the left and rises on the right. Next, we can begin to find our x-intercepts by finding the zeros of the function. Now, here's where this problem is different. To find the zeros of this function, we're going to set the function equal to 0, and we're going to solve for x. In the previous section, we were able to factor 4-term polynomials by grouping. Now, this one we could not factor by grouping. Notice these second 2 terms do not have a greatest common factor. So at this point, our traditional factoring methods are out. Grouping won't work for these 4 terms. And in addition to that, I don't have a clue like we did in the previous example. Or back up here, when we started out with the fact that this was one of the zeros, we were able to use that to reduce the degree down low enough where we could find the remaining zeros. So here's how we're going to approach this in this section. We know that the zeros correspond to x-intercepts. So I'm going to graph this function using my graphing calculator, and I'm going to observe one of the x-intercepts. Now, if you have a lot of experience with college algebra, you may have learned this from the rational zeros theorem. If you've ever learned the theorem that has P's and Q's, that's another valid way of determining a starting point for your synthetic division process. We're just going to observe our graphing calculator and pick a zero out from the x-intercepts. Notice the leftmost zero there is -4. So I'm going to start with that one. I'm observing that the graph crosses the x-axis at -4. So I know that this is going to have a multiplicity of 1. So let's go ahead and divide out -4 as our suspected zero. Now, we'll be able to confirm this using synthetic division. So again, we obtained -4 from the graphing calculator, kind of as an educated guess to begin reducing our polynomial. And we will verify that here with synthetic division. Hope you're getting used to that synthetic division process. Notice we have confirmed that -4 is one of the zeros. So what does this mean? Remember, we are looking for 3 zeros at most. Expect at most 3 zeros. We have found one of the zeros. Let's find the other 2. Notice this is degree 3 to begin with, so now we know this is a degree 2 polynomial. So I'm going to reassign my descending powers of x and then factor this one in the traditional way. You can either factor or you can do quadratic formula. Now, if you sit down and work on this one, you're going to find out that it factors like this. X minus 1 times x minus 1 equals 0. Or you could write that x minus 1 quantity squared. So I'm only going to get 1 0 out of this part, but I observe it is multiplicity 2, so it's going to count twice. Let's go ahead and fill in our information over here. The first 0 that we found was -4. It has multiplicity 1, and the graph therefore crosses the x-axis there. The other 0 we found is 1, and it has multiplicity 2. At a 0 of even multiplicity, the graph is going to bounce. And that accounts, when I sum the multiplicities, I get the degree, so that accounts for all of the zeros, and this therefore is just extra space. Now, do you remember the shortcut for finding the y-intercept? Remember, I can look out here at this constant term. If I set all these x values to 0, that would be the only one remaining. So our y-intercept is x equals 0, y equals 4. Okay, let's transfer this information to our graph. I'll start with my y-intercept, 0, 4. I'm going to make some notes here. The left end falls and the right end rises. And it's going to cross the x-axis at -4. I'm just going to put a C for cross. And it's going to bounce at 1. Now remember, when we approach these graphs, we're going to put all of these clues together to come up with a pretty good sketch of our graph. Got a cross here. I'm not sure where it turns around, so just going to make it turn around somewhere. We know it has to bounce here and then rise beyond that. So that's kind of my sketch. And then we can clarify that with our graphing calculator. Notice the maximum there is again above our viewing window. So we know to draw our graph just a little bit steeper. It turns around up there somewhere, crosses here, bounces, and then rises beyond that. Okay, so in this particular problem, it's kind of a sneak preview of where we're going. We could not factor this by grouping, so we used our calculator to take an educated guess about one of the zeros. We were able to confirm that with synthetic division, and this reduced our polynomial down far enough to our comfort zone where we can just factor it directly. Then we were able to break it down, find the remaining zeros. Combining that with what we know about multiplicity, we're able to get a pretty complete graph for that polynomial function. All right, you're ready to begin your homework for section 4.2.